Those are skills.
Okay, so today we are going to do the rest of the logistic regression chapter, hopefully. And then next time on Monday we will start chapter 15. Now you may have noticed that chapter, well, if you bought the paper version of the book, you've probably noticed that you're now out of chapters. Right? After chapter 13, you're at the end of that book. And so now from here on out, 14 through 17 are electronic only. So if you don't have access to the e-book, then your book should have come with a CD or something that has PDF files. Does yours have that?
I've used the online book.
Okay, so you have the e-book. Yeah, if you have, well, I guess everybody has the e-book because you had to get the launch pad. So you'll have to rely on the e-book only from here on out. Okay. Yeah, it's wonderful. So logistic regression. Let's bring our brains back up to speed, if that's possible, because it was before spring break that we talked about logistic regression. So
this is the Boolean regression.
yeah, it's a y variable, dependent variable that is a yes/no or a 0/1. Right? So you'll hear it called dichotomous. You'll hear it called binary. They all mean the same thing. Right? There are 2 or 3 different main statistical methods for doing regression with that kind of data. Logistic regression is the most common. There's also something called probit. You don't have to write all this down, but there's something called probit regression, which is very similar. Results are almost identical, but it's done in a slightly different way. And then there's a Poisson regression that also can handle this kind of data. This class won't get to those things. We'll talk about some of those things in regression class 346.
Can you write down how to spell the other one?
Now you can look it up.
I don't even know where to start.
Just Google it.
It sounds French.
Poisson, it is. It's a guy's name. That's the French word for fish. So
Fish.
his last name was Fish, but Poisson sounds better.
Interesting.
So anyway, what's the tactic we use when we try to fit a regression model to data that's 0/1?
Are you referring to the odds?
Convert to odds, then take the log of those odds, and then
Yeah, log it.
log it. Right? So that's called the logit transformation. You log it. Right? So it's log ln for natural log.
Does it matter that we're using natural log? Instead of log base 10?
No, log base 10 would work, but it's not as handy.
Okay.
And the software packages like SAS or whatever, they all do
Okay.
natural log. But really any base log would have the same effect. So log odds. So I'm kind of writing this out more as a sentence, but log odds of y equal 1 is equal to a regression, a linear regression type model. So beta 0 plus beta 1, x1 plus ... however many x's you have. So we'll call it beta k, x of k. Right? Now I mentioned last time that there is no error term in a logistic regression model. Right? Do you remember this? Why is there no error term?
Assumed to be 0.
Well, error terms are always assumed to be or have expectation of 0. So that's not it. But why is there no error term?
Because you can't have, if there's error and you're saying yes, then it's probably no, or vice versa, right?
Well, not exactly. That's not exactly what's going on. In regular regression, over here is y sub I, right? That's the y value for the ith person, or the ith object, or subject, whatever it is. What is this? Well, it's odds of yi equal 1. So now that's a group statistic. You can't compute the odds from a single observation. So you've already had to pool your group together or whatever, so there is no error term. There's no residual for a single person. Right? So, as such, we fit the logistic regression model just like we would multiple regression, but no error term, and we've done this logit transformation. Okay, so do you have in your notes the example that we were doing last time? That was binge drinking among college students. Remember this?
Oh, yeah.
Yeah.
Yeah, and so we did conditional proportions and all those things, and I don't think we got really far into it, but I'm gonna put the table back up here. We have men and women, and then the binge response variable is yes, no, and we're gonna say yes is a 1 and no is a 0, and males are 0 and females are 1.
Oh yeah, it was 50, 50, 50, and then 200.
No, not for this example. So the men that said yes, they have binge drunk,
Yeah.
binge whatever, right? Was 1,392, and then 3,956 said no, for a total number of males in the sample of 5,348. And then for females, it was 1,748. See, I know females are more likely to binge drink. Oh, but wait,
That was where you
there were 8,471 females. So it's actually a lower percentage, which is kind of what you would expect, knowing you guys. Okay? So we did conditional proportions last time. So the probability of a yes given a male. You remember what that was? Do you still have it in your notes?
0.26028.
0.26028. And the probability for females is 0.20635. Okay? And then did we go through the process of converting to odds? Have we gotten that far?
Yes.
You're shaking your head no, everybody else is
I
like,
don't remember.
well, it was
Yeah,
a
it
week
was
and a half ago.
It was just this one over the top of 1 minus the
Right.
same thing.
So to convert this 0.26 into odds, you take probability of yes divided by probability of no. That's the definition of odds. So you take 0.26 over 1 minus 0.26, right? So I won't write all that out, but so odds of yes given male
35187.
0.3, okay, 0.35187. I actually have a 6 in my notes, but out that far it's not going to be. So the odds of a yes given female is
0.26000.
0.26000. Okay. Now the typical thing, since logistic regression deals with odds, then the typical way of explaining the results to your audience is to talk about odds ratios, right? So, what the heck is an odds ratio? Duh, it's a ratio of the odds. So the odds ratio here is if I do males to females. So the odds ratio, we'll say OR, and then I'm going to put in parentheses males versus females. And this is, I use versus because SAS will write it that way, and it always implies that whatever comes first is on the top of the fraction, and whatever comes after the verses is on the bottom of the fraction. So if I take the odds ratio, I get 0.35187. It's not a very good 5. It looks like a 6. So 3, 5. Was it a 1/8? Yeah, 1/87 over 0.26, and then a bunch of zeros. If you multiply that out, or I should say divide that out, you get 1.35. I can't draw 5 with this marker. You'd have to pick your marker up too far. 13533. Okay? Now the interpretation of that is very similar to relative risk. Remember when we did relative risk way back in the day? Relative risk is similar to odds ratios. Relative risk is the ratio of the probabilities. So if I took 0.26 and divide by 0.2, I would have a relative risk. If I convert to odds and then take the ratio of the odds, then I get the odds ratio. But the interpretation is the same. We would say males are 1.35 times more likely than females to binge drink. Okay? Can somebody with a calculator do, I didn't do this one in advance, do the relative risk. Take 0.26 divided by 0.206. So up here on scratch paper, 1.26 something? 1.4. And so that's relative risk, right? Notice that that number and the odds ratio are fairly similar. And that's usually the case. But they become, when the probabilities get really low, then odds and probability are almost the same. When you get near 0.5 in the middle, then the two will diverge a little more. But when we do logistic regression, we are mostly interested in odds ratios. Okay? So tell me what you would expect if there was no difference between males and females for that odds ratio. 1. You expect a ratio of 1. So that becomes our null hypothesis. Right? Odds ratio equal 1. And that's the same thing as saying null hypothesis that odds for males equal odds for female. And just like always, null hypothesis means no difference. Right? There's no difference. So when you're doing ratios, no difference is a 1. When you're doing means and things like that, then the difference is literally take a subtraction, and then the null is a 0. So you have to make that switch that, okay, now I'm looking to see if a confidence interval for the odds ratio contains the number 1 or not, instead of contains 0 or not. Okay, so let's here we go. Let's actually find the parameter estimates from the model. Now, remember on the previous page that we had, I'm just going to say log odds, not write it out quite as fully as I did. But we had beta 0 plus beta 1 and that's a 0, plus beta 1 times x, and I'm going to call that, I'll call it sex. Right? And sex equal 0 for males. Okay, so the log odds for males well, wait, before I do that, look at the model. It says the log odds for a person, male or female, is equal to beta 0 plus beta 1 times their gender. And if their gender is male, this will be a 0.
So the odds is
So the log odds for males is
These are
B sub 0.
beta sub 0. You can say B, that's fine. And we're going to estimate that with little b 0. And no, not a 1. That's the null hypothesis, right? But we're actually going to fit the model and see what it turns out to be. Right? Now, if the log odds for males is beta 0, what's the log odds for female? Look at the model. What is it? Beta 0 plus beta 1. So how am I going to get estimators of those things? Well, on the previous page, we computed the odds for males. So all I got to do is take the log of it, and I got an estimate of beta 0. So B0, or beta 0 hat, I sometimes write, is the log odds for males. So let's go back to that page real quickly. And the odds for males was 0.35187. Take the natural log of that number.
Oh man.
Negative 1.0445.
Negative 1.0445. Like that? Okay. Now, how do I get an estimate of B1?
Use the beta 0 value.
Use the estimate of beta 0 that we just computed, plug it in right there, right? So what is the log odds of females? I got to go back and show what the odds were. The odds for females were 0.26 and then 3 zeros. Is that right? That seems odd for real data. I guess
It's negative 1.3471.
negative 1.3471. Okay? And that's equal to beta 0, which we've now estimated as negative 1.0445 plus B1. Now I'm replacing the betas with the B's because now we're estimating. We're using sample data to estimate those. Right? So now solve for B1, and you get B1 equal come on, you can do it. I'm not going to do it in my head.
Negative 0.3026.
Oh, yeah, I was going, no, I don't have a negative in front of it. But in my notes, I had females were 0. And all it does is reverse the sign, which we can show in stats here in a little bit. So, negative 0.30257, is that what you got? Okay. Okay, so there are our two parameter estimates. So what is our model that we're going to use to predict with? Well, let's write it down here at the bottom. Actually, let me just go to another page because my camera's not hitting the bottom very good. So the log odds is equal to beta 0, which is, that was the negative 1.0445, and then minus 1.34707 times 6. Right? Now, I may have changed some decimal places on you. Is that what we had before? Negative, or 1.34707?
That's the log of the odds of female.
Oh, yeah. Which is, makes sense that I have that written here because I had flipped it. That was my, so it's the 0.3, it's this, right?
Yeah.
So 30257. And it's negative, so I already had that point, 30257. Right? Okay, now, an interesting thing happens when you're dealing in the log scale with these parameter estimates, and it's why we are interested in odds ratios and not differences in odds, because of this little nice thing. If I take e to the b1 power, that's e to the negative 0.30257, what do you get?
.7389.
0.7389. Okay. And it's not what I wanted it to be. But if the negative wasn't on there, remember when you have log scale, a negative, you can take an exponent out front or all that. But take the reciprocal of this. Take 1 over 0.7389.
1.3533.
1.35.
33.
34.
Okay. Does that number look familiar?
Mm-hmm.
Yeah.
We just
Yeah,
undid
that's
what we did.
one of
That's the ratio.
1.3533. That's the odds ratio males to females, right? So then when I did the model, I flipped them, and I got e to the b1 as the odds ratio. This is females versus males. Is that an M? Females versus males odds ratio, OR. Right? This is males versus females odds ratio. Obviously, 1 over a ratio is the ratio going the other way, right? If we had set it up so that males were 1 and females were 0, then we would have gotten this as our answer when we did that. So you can always get from one to the other just by taking the reciprocal. Okay? All right, so now let's go to SAS and run this model. And right now, just to make it fast, I have already written SAS code, and I'm running this in SAS, not SAS Enterprise Guide. But at the end, if I have time, we'll go into Enterprise Guide and actually run this again, right?
Does it work?
But
Did they fix it?
it is fixed.
Oh, yes.
Yeah, it is fixed. So the first thing I wanted to talk about was that SAS will allow the data to be set up in 3 different ways. All right, now, so for this particular example, notice that doesn't work, does it? In this example, here are the numbers that we had in the 4 cells of that table. So this way of setting up the data, you input the gender variable. I called it sex a minute ago. So gender, binge, and then the count. So the count is just the frequency in that cell, right? So gender 0, and I know for sure this one's set up with 0 is males, right? So 0, so this is males. That binge drink, yes, 1,392 of them, and so on, right? And then this way of setting up the data is what SAS calls the events trials way of organizing the data. So it's set up with your grouping variable gender, and then the number of events. Okay, what's an event? It's like
Likely to happen.
yeah, it's what it is you're counting. How many of them did this? So it's the event is a yes. It could be an event like somebody died. That's where the word event comes from. They've had the event, right? They've died, or they've contracted the disease or something like that. But so event and then trial. So that number 5348, where did that come from? Total number of males. So if I add 1392 and 3956, I get 5348. So you can set it up either way. You can give it the number in the column that you're interested in and the total number, and then, or this way, and I had to just create do loops to do it. You can have a data set that has one record for each subject. And a lot of data sets will come to you that way, that you're going to analyze. Like if you're analyzing data on automobile insurance, then the yes-no variable that you'd be interested in is whether or not this policyholder had an accident last year. Did I have to pay out a claim to this person? Right? So that's my yes-no variable. But I have a single row in my spreadsheet for every policyholder. It might be 10,000 of them. Right? So you got a policyholder, you have all their characteristics. Are they male or female? It makes a difference in their likelihood of having an accident. Are they young or are they old? That makes a difference. Do they drive a red sports car or not? Right? So all those would be those X variables. And you're trying to predict whether or not they would have an accident. Guess why you'd want to know that if you were an insurance company?
What?
Why would you want to know that? Why would you want to do an analysis like this if you were an insurance company?
You can set your rates.
You set your rates. You can predict the probability somebody's going to have an accident, and if it's pretty high chance, they're going to pay more for their insurance.
Which is garbage.
No, it's not garbage.
Oh.
Why should a good driver like me?
My insurance went up $300 when I got a new car, and I've never been in an accident.
Doesn't matter how good a driver it is, it matters how bad they are on the road.
No, it does matter. That goes into it, but if they're a bad driver, then you got both things working against you.
both
So
things.
it matters, right?
Yeah.
And getting a new car, that's one of your X variables. How much did this car cost? If I'm going to insure this car, if it's an expensive car, you got expensive insurance. If it's a 1979 Subaru like I drove in college, with dents all over it, then, and the reason the dents were there we won't talk about, but my insurance was pretty high even on that car for that reason, right? So all those are your X variables, but you'll have one record in your data set for each person with all those variables. Right? So that's set up like this. So I created these do loops to create a data set like that. And if I run it and then print it out, you'll kind of see why it's not that handy to have your data set up that way if you can get by with one of the other ways.
You're just gonna have a bunch of ones and zeros.
Exactly. So
Well, pretty nice.
it's still thinking, I should have known better than to run something on this machine in front of the class. There it is, right? So observation number 1 was a female. And they said, yes, they binge drink, right? Now I had to do this, they're sorted by that. But there'll be, you know, however many thousand, 1,700 I think, females that said they binge drink. And then, so this whole data set's going to have how many observations in it?
13,816.
13,000. So let me go Control End to get to the bottom. 13,000. This is observation number 13,819 was a male who does not binge drink.
That's not wrong.
Right? And so having the data set up like this, you've got a huge data set if you've got a big sample. But you know, internally in the computer, that's fine. It doesn't affect anything. But, okay, so then I have some code here. And I'll run this code. It says proc logistic. Remember in SAS, proc is short for procedure. So this is the logistic procedure. And I tell it what data set I want to use. And then the word descending, I'll show you what that does in a minute, but it tells it whether you want to model a yes or a no. And you can control it by whether you say descending or not. And descending, if it's a numeric variable like ours is, our binge is a 0, 1 numeric variable. Descending says use the lower value, predict the probability of that. Without the word descending, it would predict the probability they say no. And I want to predict the probability they say yes. It doesn't really matter mathematically. You can get from one to the other. But to match what we did a minute ago, I need to say descending. So I will hit the little running guy. I keep forgetting I can touch the screen and do it. It's over there. And again, it's going to think for a little bit. But then it gives output. So let me scroll up to the top. The output in SAS will give you some information about your data set. So this is to look at and make sure it looks like it's supposed to. If you get weird numbers in here, then something's the matter with your data or whatever. Right? So it tells me what data set I used, what the variable was for my Y variable, the response variable, how many levels it had. It's possible to do logistic regression when you have more than 2 levels, right? What it then does is predict the probability of being in a higher valued class. It assumes there must be an order to them, right? So ordinal data. We won't do that in this class. We'll only do the dichotomies. And then you can change what kind of model you want it to fit, but the default is binary logit. So that's what we're going to do. But I could tell I want to do a probit model or the Poisson or something like that. Okay, so number of observations, and then the response profile means, okay, how many had yes, they binge drink, and how many had no. So it was 3140 total, males and females together. And then this kind of a model, a non-linear model, is fit using what's called maximum likelihood estimation. You don't have to write that down or remember that, but it's not least squares estimation like we're used to for regression, right? Least squares regression can be done in a single closed form step, right? You've got a formula, boom, plug it in, you get a number out. Well, nonlinear models, most nonlinear models can't be fit that way. There is no closed form solution, so you do this numerical algorithm that converges to the right answer. So it'll tell you the iteration history. It'll say model convergence status. The convergence criteria of 1 times 10 to the negative 8 has been reached. Right? So you always want to check that. Almost always it'll converge fine, but once in a while if you get some odd variables in there, it might keep the model from converging, but it'll give you warnings if that happens. It'll say, warning, model didn't converge, you may not want to use it. Okay, so this part of the output, testing global null hypothesis, and then capital beta equals 0. This is just like in multiple regression model, we have that, what we call the overall F statistic at the top. And it was just the whole model. Is this model a good predictor of the Y variable? And that's what that's testing. So if you've got 5 X variables in your model, this one's testing that all 5 of these together help predict or are significant predictors of, right? So it's the same thing that at least one of the variables is significant. Right? Not that they're all significant, but at least one of them is helping. Highly significant. So we only have one variable. So in this case, that's going to be exactly the same p-value as for gender down here. But when you're rounding that far out. But notice that the Wald chi-square statistic for the global null is 54.112. And down here it's 54.112. It's because there's only one X variable in the model. Right? If I had more variables, then they wouldn't match. The overall one would be all of them combined. Okay? So now look at the parameter estimates here. Do they match what we did a minute ago? They're backwards, right? What did we have for our intercept? It was negative 1.44 something?
Yeah. 1.04.
That, say it again?
And that be at the mailable one, I guess that's our intercept for
Yeah, and I have a positive for the gender for the B1.
So that's just flipped it like you did.
Yeah, now let me go, I need to check. I forgot to point out this line says probability modeled is binge equal 1, and that's what I want, so I have that correct. But you can also tell it, you can give it the descending command on the model. No, you can't. Not the way this is set. If you use it as a class variable, then you can. I'm a little confused now because let's think this through. What would I have had to do with the model? I want to get back to my notes a minute. I have to use the mouse to do that.
It's just females and males flipped.
Yeah. Isn't the female and male just switched?
Because that beta 0 that I had for that was what we got for the odds
For
of
female.
for female.
Yeah.
Right. So we had this as our beta, and that's the odds for females. Right.
That's the odds for males, but
That's the
But
the
the
one
one-
in SAS is
the one in
for
SAS.
females.
So
the 1 and 0 are.
yeah. But I swear, let's look at it. I swear when I looked at the data, or the table, oh, but I ran it on this data set. Maybe I have it set wrong. If gender equals 1, then I use 1392 as my number. I flipped it.
Yep, you flipped it.
Yep.
Yeah, so I put gender equal 1 is males. So I'm going to rerun that. I'm going to fix that and rerun it. Because I want it to match what we did a minute ago. It bothers me. So I'll rerun this data set. Don't need to print it. And then rerun the logistic regression. And now our parameter estimates match what we had before. So that was a nice little exercise to show you that, look at the test statistics. They're identical. Nothing changed. So your conclusions don't change, but if you re-parameterize how things are set up, you'll get different estimates, but the conclusions don't change. But your interpretation of them must change accordingly, right? So now look at the odds ratio. That was the 0.739 that we got when we did it before we flipped it over, right? So that's females to males, right? Now, if you take on your calculator e to this power, you already did it, so you don't have to redo it. You get that number, right? Now, what about these confidence limits? Let's talk about that. Up here, it gave us the parameter estimate, and it gave us a standard error of that estimate, right? So, let's see, I need to go back so I can write on the screen. I need to click that button, and that always gets me in trouble.
You're gonna want the
Mouse pointer.
the mouse button.
This one?
Yep.
There. And now I can click back on that button, right?
Yep.
Okay, so if I take this standard error, so I'll just come through over here. Gender is negative 0.3026. Now go plus and minus 1.96. Does that number sound familiar? What is 1.96?
It's a T statistic.
It's a Z critical
It's-
value,
Yeah, it's a Z
right?
crit. Yeah.
And since they're doing chi-squares, if you take a standard normal and you square it, you get a chi-square. So I know that's how they're doing their standard errors. And since they use the word chi-square, I know it's a Z, not a T. Usually in regression, we deal with T's, but that's ordinary linear regression. In nonlinear regression, it's back to Z's. Right? So that's a little confusing at first, but then 0.0411. All right, do that for me real quick on your calculators. Do negative 0.3026 minus 1.96 times 0.0411.
Negative 0.38316.
38316.
Yep.
Okay? And now do the plus.
Negative 0.2220.
Negative 0.2232s
Yeah.
and then 0. Okay? Now, exponentiate each of those. All right, so take e to the negative 0.38316 and e to the negative 0.222.
The 0.222 is 0.80088.
0.80, say it again?
088. Another 0.
Another 088. Okay? And then this one is e to the negative 0.38316.
0.6817.
6817. If I make an interval out of that, there's their confidence limits, right? So all they're doing is they're putting a confidence interval on the parameter in the log scale, and then they're back transforming from the log scale to the linear scale and transforming both the parameter estimate. E to the parameter estimate gives me the odds ratio. Lower bound of this confidence interval, e to that power gives me the lower bound of the odds ratio, and so on. Yeah.
So you'll always use 1.96 since it's using chi-squares.
Yeah. If you're doing 95% confidence, then you always will be. You use one of the other Z critical values if you want to change your confidence level, but it's always a Z critical value. Okay? Now, what if I want to flip this over, and I don't want to say, this is harder to interpret when your odds ratio is less than 1, because remember the interpretation of odds ratio? So, how would I interpret 0.739? It's females versus males.
For every one male, there's 0.739 girls who are binge drinkers.
Okay, that's a good way to say it. He said for every male that binge drinks, there's only 0.739 females that binge drink, right? So a lot of times people take 1 minus that number, since 1 is the null, 1 minus that, and let's see, 7.4 would be what, 2.6? So there's a 26% reduction in the odds of binge drinking for females. That's one way to say it. Or it's perfectly fine to say females are 0.739 times as likely. But when it's less likely, saying it that way just doesn't sound right. So it's perfectly fine if you get SAS output like this. I do it for clients all the time. To take the reciprocal of it and give it to them the other way. And just say, males are 1.35 times more likely, whatever that number was. Or a 26% reduction in the odds of binge drinking for females. Okay, I've got 2 minutes left, so I don't have time to show you in how to do it in the enterprise, because I want to run this real quick. This is a model on the high GPA data that we've been kind of talking about. And I'll have to finish up with this next time, but this is an example where you have more than one X variable. So the same thing, we have gender, sex. So I have an intercept, I have sex, and then I have their SAT math score and their SAT verbal score. Right? Now, the way we've been interpreting, the odds ratio was females to males. And that's still, as soon as we get the odds ratio part of the output, we get a 1.35, right? So, high GPA. They just put a cutoff on GPA, and they said, if you're above this, you have a high GPA. If you're below this, you don't. So they converted it to a yes-no variable. And they wanted to know, what are the predictors of having a high GPA? Right? So I don't even know which is which, males or females. Odds ratio is 1.35, so one of the two genders is 1.35 times more likely. Right? But what about SAT math? We get an odds ratio of 1.004. Is that statistically significant? Well, look up here. SAT math has a p-value of 0.035.
So it's significant.
It is statistically significant. So your SAT math score does help predict whether or not you have a high GPA.
But sex doesn't.
But sex is actually not significant. It's got a much bigger odds ratio. How come it's not significant when this one is significant?
Probably because it got eaten up by the other one like you were talking about.
No, not necessarily. Because all of them are variables added last. Right? So after controlling for gender and verbal score, the math score is statistically significant. The key thing you have to realize is when you have a continuous variable for your x variable, the odds ratio is the odds of having a high GPA for a 1 unit increase. So if you score 1 point higher than I did on your SAT math, then your odds increase by this much in the log scale. You are 1.004 times more likely. So it seems like hardly any change at all, but it's statistically significant because it's only a 1 unit increase. So a lot of times what we do is we take these parameters and say, well, you know, a 1 unit increase in SAT, what's the SAT have? About 600 as a max score. So at least a 10-point change would be, you know, more meaningful. So you can multiply that number by 10 and then exponentiate, and you get the odds for a 10 unit increase. You can make it whatever unit you want. Right? So a 1 unit increase doesn't always look impressive, even though it's significant for continuous variable. But continuous variables, that's the take-home message. Continuous variables, it's per unit increase. That's what this odds ratio is. For gender, it only had 0 and 1. That's a 1 unit increase, right? But, all right. So we'll see you on Monday. Have a great weekend.
So for